Hello, good morning, good afternoon, good evening, everybody, wherever you might be. Today we welcome Arizona in Warsaw. So Jack Spielberg will tell us everything and more about relative graphs and pullbacks of relative Toeplitz graph algebras. Jack, the Zoom is yours. Take it away.
Okay, thanks, Piotr, and thanks for inviting me to give a talk in your seminar. So this is joint work with Sammy Brooker here at ASU. I should say that this is all coming from a paper that Piotr wrote with Sarah Resnikoff and Mariusz Tobolski several years ago now. And we spent some time working on it and have some. So I'm going to come back to this at the end of the talk, but I won't be mentioning this until later on. I wanted to say it now, so you know that's what's going on. And this is really a talk about graph algebras. So I'm going to begin with the introduction to what they are. Partly this is because I've come to use the opposite convention to the one that many people, including Piotr, uses. And I remember when he gave his seminar talk in Arizona, I was constantly trying to switch between two systems. And so I'm going to play the same trick backward. And so I'm going to go through the beginnings of that now to make it, if any, hopefully a little bit easier. And now, of course, there's an immediate dysfunction of equipment. Pardon me just a minute.
Okay, we see your screen.
Yeah, but it's frozen, isn't it?
No, it moves.
Only under duress. I can't swipe, it seems. You know, it's something's really quite wrong. Well, embarrassing. I don't know if you can see that
Yeah, I see everything. Yes.
Yeah, I just you know, usually you tap on something and it opens up, and now nothing's happening. I may have to shut my tablet and start over. I'm really sorry. I don't know what's going on.
Such things happen. You know, once we had with the child disconnected speaker's internet during his talk. So.
Oh yeah, well that's less blameworthy than what happened to me now. Okay. Okay, so I don't know what's going on. So am I no longer connected?
You both are connected. Jack's tablet and you, both are connected.
Right, so why is my tablet not showing my screen? Maybe the screen share stopped. Let's try that again.
Yeah, you have to share screen again. Yes, screen sharing stopped, that's for sure. Yes, I can see your screen now.
It's getting there.
There is a warning message about your screen broadcast, but it comes from you. It's not from us.
Yeah, no, I understand. Now I'm sharing.
Yep. Excellent.
Okay, now I have this. Okay, now I'm able to move my screen.
Yep.
Okay, so what's a directed graph? So it's just the diagram of dots and arrows, like this one, for example. But the convention I use, I call the Australian convention. So you should think of arrows as representing functions. The dots might be the sets functions map between. So when you write a string of arrows, say F1, F2, F3, F4, am I still doing? Yeah, so for example, we write this, that's really a composition of functions. So often we might say this is F4 followed by F3, followed by F2, followed by F1. So first the function F4, then F3, then F2, then F1. So we would move in that order. But of course, we read from left to right. So we read this as F1, F2, F3, F4. And so this is the basic mental gymnastic you have to do in order to think about how to write things like this. Okay, formally, of course, it's a quadruple, a set E0 of vertices, a set E1 of edges, and two maps S and R from the edges to the vertices that identify the source and range of an edge. And here's a little picture to remind us what that means. The source of the edge is where it begins, the range is where the arrow points to. And then a bit more notation, I use EN, E upper N, to be the paths with length with N edges. For me, all graphs are directed, all paths are directed, so I won't always say directed. And we'll use E star for the set of all finite paths. And E infinity are the infinite paths. Now, of course, you have to think about in which direction infinity goes. And so I like to call this source word, meaning they extend infinitely far toward the domains of our functions or the source of our edges. And then a convenient notation is something like this one, alpha E star. If alpha is a path, then alpha E star is all the paths you can form by combining alpha with something else to its right. So all alpha beta where beta is a path. I like to think of these as extensions of alpha.
By the way, if I might jump in with a quick comment, in fact, you have a very beautiful semi-ring structure on the space of all finite paths. I mean, you take subsets of a set of finite paths, and you can multiply them exactly the way you just described, and you have a nice semi-ring structure, with the set union being the addition and this being the multiplication. And it very much reflects later on what happens with path algebra.
Sure, it's exactly what's going on. And in fact, when of course, you multiply two sets, and it's only certain products that are existing because the range of the, well, domain and range of functions, domain and codomain have to match up.
So you have zero divisors. You can multiply two non-empty sets into the empty set.
Right. Okay, so here's back to the specific example. Let's focus on this colored dot here for the moment. That's the range of the edge E1. So if we look at the set R of E1 E star, that's all the paths whose range is the same as the vertex R of E1. So what paths have range R of E1? Well, we could start somewhere out here and move down until we get there. That would be, say, EJ followed by EJ minus 1, dot, 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 followed by E2, followed by E1. Or we would write that just as E1, E2 up to EJ. Once we've gotten to this dot, we can go around this loop as many times as we like. That's, so now, really, if we're reading E1, E2, E3 up to EJ, we read from against the arrows. So we have to read this loop against the arrows, F5, F3, F4. And that's how we see it here. Of course, that means F4 followed by F3 followed by F5 as composition. So we could run our way down from somewhere out along the E's and then a finite number of times around the loop. That's this first collection. Or we could start at one of these dots and follow one of the G edges and then follow F5 to get to this dot. So that looks like this. And then again, we can run around the loop as many times as we like. Or we could just follow F5, then around the loop, or F3. These are all the finite paths whose range is the same as range E1. So that's the meaning of this kind of notation. If we look at the infinite paths that have range E1, R of E1, so an infinite path, well, we could, let's see, what can we do? Well, we can run around this loop infinitely often. That's one infinite path. Or we could run infinitely far along the E's, all of the E's. So that will be this infinite path. And then when we get to here, we could run a finite number of times around that loop. So that will be these things. So these are just supposed to illustrate what these two notations mean. And again, it's very standard. If you've done any work with graph algebras, you're used to this. But just trying to get the orientation comfortable to get started. Now, a bit more notation. If we look at the sources of the GJs, those are these blue dots. These are special vertices in that there are no edges coming into them. right? If we look at E1, the edges of E that have ranged the source of one of the GJs, that's the empty set. So vertices like this are called sources. If we look at this grayish green dot, that's a special vertex because there are infinitely many edges that have that vertex as their range. So we call such a vertex an infinite receiver. The set of edges with range equal to S of F5 is infinite. So vertices like these, sources and infinite receivers, are called singular vertices. And any non-singular vertex is a regular vertex. So we have we can use notations like this to describe the sets of those vertices in the graph E. I'm going to come back to this last thing later on. I just thought I'd mention it now. The boundary of the graph is defined to be all the infinite paths together with all finite paths whose source is a singular vertex. And as we'll see later, this is a locally compact Cantor. That's incorrect. Sorry. It's a zero-dimensional Hausdorff. So it doesn't have to be a Cantor space. I went away with myself there. But the point of this is we can think of the infinite paths and the paths whose source is a source. These are somehow the maximal paths. They can't be extended any farther. That's the natural notion of a boundary of a graph. But it won't be a locally compact Hausdorff space. You have to include in the finite paths that end at infinite receivers in order to complete it to get a locally compact space. So that's the importance of this space. Okay, once we have a directed graph, we form the graph algebra C star of E, sometimes called the Kunz-Krieger algebra. So it's defined classically by generators and relations. There are two families of generators: projections P sub V indexed by the vertices, and partial isometries S sub E indexed by the edges that satisfy these four relations. We call them CK1 to CK4. So these really show that these generators are supposed to mirror the properties of the vertices and edges. So if we look at the partial isometry SE, this says that its initial projection is the projection corresponding to its source. Now, if we look at the third relation, it says that the range projection of SE is a sub-projection of the projection at the range of the edge E, P sub R of E. So if we go back, let's see, to this picture, so the edge we think of as a function from the source vertex to the range vertex in some sense. Well, the partial isometry corresponding to the edge should have its initial projection here and its final projection here. And the fundamental asymmetry of this graph algebra construction is that while the source projection of SE is the entire projection at its source vertex, the range projection is a sub-projection of the projection at its range vertex. So there's this difference between source and range that plays out in the algebra. Now, if you have two partial isometries that, well, if their range vertices are different, then of course their range projections are sub-projections of pairwise orthogonal things. Let's see, so
Jack, if I might again quickly jump in, I'm very happy with this condition CK3 because this replaces this awkward condition with inequality that people used to write. And it's, and it's completely equivalent. And I love it this way because this way it shows how graph sister algebras come, in fact, from Leibniz path algebras, how they come from path algebras. Okay, so when you start from path algebra, this relation 3 is immediate because the relation in the path algebra already. So I'm very happy about it. And it is fully equivalent, you can prove, but it's really this 3 is equivalent to this inequality, which is in the usual definition of a graph sister algebra. So this is excellent. And
I should say that there are many different ways of formulating the relations
Yeah,
that are
but
equivalent to
that's
each other.
sort of for me the nice way to do it. This is the way I advocate it. And also maybe it's worthwhile to mention that when you look at CK2, you can actually skip what happens for different edges, provided your graph is row finite. Then you can.
Right. So I was just noticing there's a slight mistake in this. So yeah, the second relation tells us that any two partial isometries for different edges have orthogonal ranges.
Yes. Yeah, you can skip it if you are row finite. Yes.
Yeah. Well, but we want it anyway. Now, the fourth relation is sometimes called the Kunz-Krieger relation, and it says that if you have a regular vertex, right, so that
that's the biggest troublemaker.
There are so it's a non-zero finite sum here. Then the range projections of the edges coming into that vertex fill up that projection.
Yeah.
Now, what's bothering me, I realize, is that there's nothing in here that forces projections at different vertices to be pairwise orthogonal.
Don't you assume it from the start? Yes, there should
Well,
be
I
where
should.
these are orthogonal projections, yes.
Pairwise orthogonal.
Pairwise orthogonal projections, that's how I write it usually, yes.
Yeah.
Yeah, you have to assume it.
Yeah. Now, your comment about row finite is really important because, well, so let's move on to the next slide. We also have the Toeplitz graph algebra, TC star E. And these were actually introduced by Kuntz in his very first paper. I believe, maybe I'm wrong there, I can't remember. Anyway, so we just omit the fourth relation. So if we look back, that's the relation that says the ranges at a regular vertex have to fill up the range projection. Well, if you have if you don't impose that, then there's some room between them. And then we could no longer use the fourth relation at a regular vertex to get the second relation. So it's important to have that second relation for this more general algebra. Now, in this case, the difference between the projection at V and the sum of the ranges of the edges going into V at a regular vertex, that's sometimes called the gap projection at V. And that exists in this Toeplitz graph algebra, but of course, it's killed off in the graph algebra by that fourth relation, CK4.
Yeah.
And now, lastly, we make a new kind of algebra in between these two extremes. So choose arbitrarily some subset A of the regular vertices. And then we can make this new relation TCK4. So we just invented this notation, where you impose the fourth Kunz-Krieger relation only at the vertices in the set A and not the others.
By the way,
and
maybe so it's worthwhile to mention that in the algebraic world, they are called Kohn, C-A-O-H-N.
Right, Kohn, yes.
Yeah, relative Kohn algebras.
So we have this new algebra, TC star E comma A. We call this the relative Toeplitz graph algebra, where we use the three relations that give us the Toeplitz algebra and this partial fourth relation imposing the Kunz-Krieger relation only at the vertices in A. So these relative Toeplitz graph algebras have been studied by many people. So I wrote a paper about them. Paul Muley and Mark Tum-Ford wrote a paper about them. Soren Eilers and Takeshi Katsura wrote a paper. Aidan Sims generalized this to K-graphs. And as Piotr mentioned, these relative Kohn algebras were discussed in this book by Abrams, Ara, and Siles Molina, the algebraic case. And undoubtedly, there are other people who have done this. I just am way too ignorant to know everything. And we can notice that the Toeplitz graph algebra and the graph algebra are special cases of this construction.
Yes.
For the Toeplitz algebra, we impose the Kunz-Krieger relation nowhere. And in the graph algebra, we impose it at every regular vertex.
Exactly.
Okay. Now, what we're going to talk about is dependent upon certain ideals in these algebras. And so let me give the basic idea of this, which again is very goes back to the beginning of the study of graph algebras. So talking about ideals in the Toeplitz graph algebra, if we have an ideal I in the Toeplitz graph algebra, and if we choose a vertex V whose projection belongs to that ideal, then we have the following property. If you take any path alpha whose range is that vertex, then the projection at its source is this operator S alpha star S alpha. But S alpha is the same as PV times S alpha. And that's really that third relation, that the range of a partial isometry sits underneath the projection at its range vertex. Well, I should say that if you have a finite path, we use this expanded notation. S alpha is the product of the SEIs for EI in the path. So, of course, once we know that PV is in the ideal, this product is in the ideal. So the projection at the source of alpha is also in the ideal. So having a projection belonging to the ideal is inherited from range to source of paths. So if we look at the set of all vertices whose projections are in the ideal, let's call that H for the moment, that has this property of being hereditary. Namely, all the paths whose range is in H also have their source in H. And this is just a convenient way of using our notation of multiplying subsets of paths to describe this hereditary property. Okay, so now there's a basic theorem. This is now this is an elementary theorem because so much fundamental work about graph algebras is behind us. If we start with a hereditary, sorry?
Jack, if I might again, sorry, because I love that subject. This is why I'm having so many comments. I don't know if you have ever met it in the literature, but one of my postdocs, when listening to my lecture, asked me a question. When you would take the family of all hereditary subsets, would it give a topology? And yes, it does a topology. And not only it does it gives the topology on the set of all vertices. It is the topology that allows you to define connectedness of the graph with respect to this topology, which is absolutely great because normally when you define connected graph, you use the word connected, but in a combinatorial sense. You say that the graph is connected if between every two vertices you have an undirected path. But it's awkward. You have to change your category a little bit. You have to speak about undirected paths. But being connected in this combinatorial sense is tantamount, it's equivalent to being connected in the sense of this hereditary topology. So that's really nice.
That's very interesting. It's interesting. The hereditary property depends on the direction, but the connectedness doesn't reflect that, I guess.
Yeah.
Very odd. Okay, so let's start with a hereditary subset of the vertices of a graph E. And we define a subgraph F, which I'm going to also call F sub H, a subgraph of E in the following way. We let the vertices be all the vertices that are not in H, complement of H. And the edges are all the edges of E that have source and range in the subgraph F. Now, because H is hereditary, the set F0 is sometimes called co-hereditary, which means that anything whose source is in F0 must have its range in F0. So we could write it without the F0 on the left if we wanted. Now, if we let I be the ideal generated by those projections for vertices in H, that's an ideal in the Toeplitz graph algebra, and the quotient of the Toeplitz graph algebra of E by this ideal is in fact the Toeplitz graph algebra of the subgraph F. And this, I feel this somehow, this is the fundamental construction for describing the basic work about ideals in these kinds of algebras. So we get, I call it a sort of contravariant functor from graphs to C-star algebras. So if we have a subgraph of one subgraph of another, we get a surjective star homomorphism in the opposite direction between Toeplitz graph algebras. But it's important to remember that this isn't just any old morphism of graphs. Not only is it an inclusion of graphs, but you also need these special properties, namely the complement of the vertices of the subgraph should be hereditary, and the subgraph should be the biggest possible subgraph given the set of vertices that it contains. So in this situation where we start with a subgraph having these properties, we'll write H sub F comma E for the corresponding hereditary set. Okay, so this all is talking about the Toeplitz graph algebra. We want to try to extend this to relative Toeplitz graph algebras. So Sammy and I decided to use the groupoid picture. That's another reason why I'm going to go into more background in this talk, because it's not as common for people to think in terms of groupoids as in terms of generators and relations. But I hope you'll see that there are some advantages to using the groupoid picture. So let me briefly describe how that works for these directed graphs. So, of course, I'm not going to tell you what a groupoid is. I'm sorry. But a groupoid has a unit space, a locally compact Hausdorff space. So as a set, that's just all the paths, infinite and finite, E infinity union E star. For any finite path alpha, we can define what we call a cylinder set, which are all the infinite and finite paths that extend alpha. Looks like this. And then we can define a topology on this unit space by defining the basic sets for the topology are differences of cylinder sets like this. And it turns out that this topology is zero-dimensional, locally compact Hausdorff, and these basic sets are, the cylinder sets, in fact, are compact open sets. Now, it's interesting to notice that if you have a regular vertex, you can subtract off finitely many cylinder sets. You can subtract off cylinder sets for all the edges that come into that vertex. And so we're left with a singleton vertex, which is a compact open set. Now we define the groupoid G of E. It consists of triples, alpha, beta, X, where alpha and beta are finite paths and X is any path, as long as both alpha and beta can be composed with X. So alpha and beta have the same source, which is the range of X. And we have to identify certain triples, so there's an equivalence relation to divide out by, and it's this one. So if the path X in the third coordinate can be factored in the form gamma Y, then we can move the gamma over to be given extensions of alpha and beta and use Y as our third factor. And the combinations beta X and alpha X are the source and range. And finally, we get a base of compact open bisections for a topology on G of E by using all triples where the third coordinate consists of some compact open subset of the unit space. Okay, in order to get a little bit better sense of this, I'm giving a picture of multiplication in this groupoid. So I'm considering two triples, alpha, beta, X, and mu, nu, Y. So here are alpha and beta with the same source, and X is this composition epsilon Y. Mu now is the composition beta with epsilon, and here's nu, and then Y, of course, is there. So those are my two triples. We can multiply them because the source of this triple is mu Y. Mu Y is the same as beta X, which is the range. Sorry, the range of this triple is mu Y. The source of this triple is beta X, and those are the same. So this composition should be defined. And to realize it, we rewrite alpha beta X in this form alpha beta epsilon Y. The epsilon moves over to alpha and beta. And now here we have the same third coordinate, and the first coordinate here is the same as the second coordinate here. So we just eliminate those and use alpha epsilon nu Y. What's the point of this triple? Alpha beta X takes beta X to alpha X. So it just swaps the initial segment beta for the initial segment alpha. So the second one swaps an initial segment nu for initial segment mu. So the combination should swap nu for the corresponding initial segment of this path, alpha epsilon. And that's exactly what it does. Now, if instead of X and Y, we had compact open subsets of the unit space, so we're multiplying bisections, you would do the exact same thing. All possible products out of that would give us the new element. So we can think of these basic compact open bisections as partial homeomorphisms of the unit space. So we'll take the set beta C and map it to alpha C by replacing the initial segment beta by the initial segment alpha. That's what these do. And the C-star algebra is generated by the characteristic functions of these partial homeomorphisms. Those are just partial isometries. So this is just another way of looking at the C-star algebra is generated by partial isometries. But now we have a much larger family of partial isometries because we're really allowed to use any compact open subsets of the unit space instead of just the special ones that are showing up in the generators and relations. Okay, so maybe I'll hustle a little bit. Here's some basic examples showing that SE star SE is the projection at S of E, and SES star, that corresponds to the set Z of E, all paths that begin with E. And that's the basic idea. So here we have everything that has range at S of E. Here we have only the things whose range is S of E and their first edge is the edge E itself. So in particular, the range of E, which we'll call V, is a regular vertex, then there are finitely many such edges. If we add up SE, SE star, we're really taking a union over the edges ending at V of Z of E. So that's all paths with range V that begin with one of those edges. The only path ending at V that isn't represented is the singleton V itself. So we really have this difference. And here's how we see that the characteristic function of that singleton is the gap projection of V. So this groupoid picture really gives us a very nice way of viewing all the things that have happened above, at the same time that it gives us this unit space where the dynamics happen, so we can maybe see a little bit more about what the algebra looks like. Now let's recall the boundary, which is not all finite paths, just those whose source is a singular vertex. That's a closed invariant subset. And then it's, again, not a complicated theorem to show that the C-star algebra of our groupoid is the Toeplitz graph algebra. And if we restrict the groupoid to the boundary, we get the graph algebra. It's exactly killing off the gap projections. Now, in the relative case, we extend this, we define a new unit space, a subset of the old, by throwing away finite paths whose source is in the set A. In other words, we're going to kill the gap projections for vertices in A, but not in any other vertices. And then the groupoid G of EA we get by restricting to that closed invariant subset. And the same kind of theorem tells us that this groupoid has C-star algebra, the relative Toeplitz graph algebra. So putting all the previous things into this context of groupoids. Okay, now let's begin to build back toward our general situation. Suppose we have a graph E, a hereditary subset H, and the corresponding subgraph F. So it turns out that the unit space of the graph of F, of the groupoid of F, the groupoid of F, is a closed invariant subset of the unit space of the groupoid of E. So we can think of the groupoid of F as sitting inside the groupoid of E in this way. And the proof of this is not hard, but it's interesting, I think, to see what happens. If we look at the unit space of G of E, well, it has these two parts, E infinity and E star, and we can write them this way. So the infinite paths either arise in H or they don't, in which case they arise in F. So E infinity is really E star H E infinity and F infinity. E star, well, these are paths, either their source is in H or it's in F. If the source is in F, the path is in F. So if we take the union of these two things, we get the F parts give us G of F0, and the rest of it is paths in E that originate in or arise in H. So to show that G of F0 is closed, we have to show that these other things are open. And that's not so hard. If you have any path that arises in H, you can write it as a finite path alpha combined with some path Y, where the source of alpha in the middle here belongs to H. But then Z of alpha is an open set contained entirely in things that arise in H, and it contains X. There's our neighborhood of X that proves openness. And now I have this commuting square to illustrate this. We have this quotient of Toeplitz graph algebras that we saw before, and it just comes from restricting to the closed subset of the unit space. Okay, let's now extend to the relative Toeplitz graph case. So let EH and F be as above, and let's choose a subset of the regular vertices for E and for F. And now we have still our quotient map from the Toeplitz algebra of E to that of F. We can now also quotient onto the relative Toeplitz graph algebras in both places. So does this quotient map nu descend to the relative Toeplitz graph algebras? So is there a dotted arrow here? And the lemma is fairly elementary. It says there is such a map if and only if we have this condition. The chosen regular vertices A that happen to lie in F must also be in the chosen set B. Let's see briefly why this is true. So I'm just redrawing this diagram so we can recall it. So kernels of these maps are given by, while we're restricting to a certain closed subset of the unit space, the kernel corresponds to the complement of that set. So the kernel of this pi sub f, while we're restricting from GF0 to GFB0, so what we've thrown away is F star B. And since B is contained in F0, that's the same as E star B. Now the kernel of nu, of course, is the complement of GF0. We saw that was the E star H E infinity together with E star H. So the kernel of this composition along the lower side of the square is the union of those three things. Now, pi E, we're restricting to G of E A0. That means we've thrown away E star A. And we can write that as the portion of A in H and the portion of A that's not in H, namely F0. So the map here exists if and only if the kernel of pi E is contained in the kernel of this composition, pi F composed with nu, which means if and only if this set is contained in this set. Now, the first part is obviously contained in here. Actually, it's contained in this thing. So we have containment this way. And the only way to get containment this way is for A intersect F0 to be contained in B. So this is why we find using groupoids convenient. Many lemmas of this kind reduce to showing that a certain subset of the unit space is contained in another, which is just a little set theory. It's easy to look at. Okay, now let's suppose that we have this condition so that we do have containment of unit spaces, and let's let U be the difference. So that's a relatively open invariant subset of the unit space of G of EA. Let's see what that set U looks like. This will be important later. So remember, G of EA0 looks like E infinity together with E star, well, all finite paths that don't have source in A. Now, E infinity we can break into these two pieces, right? An infinite path either arises in H or it's entirely in F. E0 minus A, well, that's, well, either it's things in H that aren't in A or things in F0 that aren't in A. And now let's rearrange this a little bit. So let's take E star H minus A and move it to the left and put the F infinity together with this other F part. And now this F0 minus A, well, that's F0 minus B together with B minus A, because once we're in F0 minus A, we're only throwing away the part of A that's in F0, and that's contained in B. So B is the larger set. And now these two blue terms together are exactly the unit space of G of FB. So we have these three pieces, and then the unit space GFB. So the difference U is exactly the union of those three pieces. I recognize this is a lot of symbols to look at, but it's a convenient way to describe what this set is. And then we have this short exact sequence for the quotient map. We've identified the unit space as the restriction to this particular open set. Okay, so let's see what's going on. Here are the suppositions or the hypotheses we need to set up our situation. So we need a subgraph F of E. We need a choice of a subset in each set of regular vertices for these two graphs. We assume that the complement of F0 is hereditary. We assume that F is maximal within within E for its set of vertices. And we assume this special condition on the sets A and B. Excuse me. So what we saw is that in these circumstances, we get this surjection of relative Toeplitz graph algebras. So we decided to formalize this in a combinatorial way. So these are what we call the relative graphs. So a relative graph is a pair, a graph E and a subset A of its regular vertices. And a morphism of two relative graphs, FB into EA, means exactly those four conditions. Right? So this is exactly describing how you get a surjection of relative Toeplitz graph algebras corresponding to choosing a certain subgraph of the larger graph. But now that we're entirely in this context of graphs, we can ask, is the composition of two such morphisms again a morphism? That's completely routine to check. I won't bother saying anything about that. But in this sense, we get what you might call the relative Toeplitz graph algebra functor from relative graph to C-star algebra, and it's contravariant because the map from a subgraph to a graph, a relative graph to another relative graph, gives us a surjection of C-star algebras in the opposite direction.
Sorry, Jack, may I ask a question? I'm a little bit about this condition number 3 in your definition of a relative, a morphism between relative graphs. Yes, exactly. I'm a bit surprised that you have F0 on both sides. Because
well, of course, we don't need it on both sides. We can eliminate it on the left because F0 is co-hereditary.
Yeah.
So yeah, it's the same. Yeah, so without thinking about co-hereditary, it's convenient to think about it this way, to emphasize that it's the maximal number of edges you can put in.
No, I'm happy now.
Oh, good. Okay, so now here's a theorem that seems completely reasonable, but I was sort of pleased that it turned out to be true. Remember, we're eventually trying to look at pullbacks of C-star algebras corresponding to pushouts of graphs. So this new category of relative graphs does emit pushouts. So this is a long diagram chase. I don't want to go through that argument, but I want to indicate what's important in this construction of the pushout. So let's start with the basic data for a pushout, namely two morphisms from one thing into two other things. So we have maps from F0A0 into F1A1 and F2A2. So we want to find this relative graph EA and morphisms beta1, beta2 into it that make this diagram a pushout of relative graphs. Pretty clear that if we forget about the relative part, we have to have a pushout of ordinary graphs. So the graph E as a graph has to be built out of F1 and F2 this way. Namely, the vertices are the disjoint union of vertices from F1 and F2, where you identify the images in F1 and F2 of a vertex in F0, and likewise for the edges. So the usual push out of directed graphs.
And when it comes to this set E, which gives you the relativity, it's also just a push out of sets, right?
Sorry, the A?
No, E. No, sorry, you wrote it. Yes, we must have. Yes. So E is just a push out of these sets, and the same then goes from the set of vertices and the set of edges. All three sets are push outs.
Exactly.
Okay.
Okay. Now the interesting part is with the relative business, of course. So it's routine to check that the complement of the Fi0 in E0 is hereditary in E, and that both of them are maximal in E in the sense that we need. All right, so what am I looking at? Yeah, so we have these three properties basically for free. You just check them quickly. The interesting thing is, what does A have to be? Well, so it's important to notice that if you look at these two hereditary sets, one for F1 and E and one for F2 and E, their intersection is empty. Because and that's really just because the F1 union F2 is all of E. This is coming straight out of Piotr, Sarah, and Marius's paper. So the picture that we like to think of is this one. So the whole diagram is supposed to be the graph E. Here in this lower left corner, we have the graph F0, just looking at the sets of vertices. And here we have the two hereditary subsets of E. So F1 is gotten from the stuff that's not in F2, and F2 is gotten by the stuff that's not in F1, along with the F0. This is a very nice way to think about where the vertices and edges are coming from. Now, if we want, let's go back to our, if we want the, say, beta 1 to be a morphism, then A intersect F1 0 should be contained in A1. And the same thing for beta 2. That's these conditions. A intersect Fi 0 should be contained in AI. Now, AI itself is contained in Fi 0. So this is equivalent to thinking of it this way. A intersect Fi 0 should be everything in AI that's not in F0 together with a portion of AI that's in F0. And if we put these together, we find that A has to at least be contained in this set, which I'm calling C. And everything in A1 that's not in F0, everything in A2 that's not in F0, and things that are in both A1 and A2. And of course, this portion is contained in F00. So this is one restriction on the set A in order to have a commuting square of morphisms of relative graphs. But now, if we use that set C, we do get a commuting square. So if EA is the pushout, there has to be this dotted arrow in this direction. But that would mean that C intersect E0 would have to be contained in A for this to be a morphism. That's just the opposite containment from what we proved. And this says that the set A has to have this property, has to be exactly this one. So there's a unique pushout in this category of relative graphs. And this formula, of course, is important for us because it tells us what the relativizing set A is for the large graph E. Now, a slightly interesting remark, this will come back to us later. For alpha 1 and alpha 2 to be morphisms, so A1 intersect F0, 0 has to be contained in A0, likewise for A2. So we get this containment, A1 union A2 intersect F0, 0 must be contained in A0. But if you notice the set E and the set A, well, sorry, the set, not the set, the graph E, the set A doesn't depend upon the choice of A0. As long as A0 contains this stuff and it's contained in F00 itself, then we have this push out. So this is somehow flipping things around. Once we've chosen the set A, now there's some choice in what A0 could have been in order that we get a push out like this. Okay, now let's use what we've got. Let EA be the push out of this in this setting. And so now we have all these morphisms of relative graphs. So we get corresponding surjective star homomorphisms of relative Toeplitz graph algebras. That's the square. Since they're surjections, they're really quotients of the upper left corner by some ideals, which I just index by the index in each corner. And what are these ideals? Well, we're just restricting to certain open subsets of the unit space, which we know how to write because we've already done this. So U sub I is, again, it may be ugly to look at, but it's not really so bad. We have functions that arise in HFIE, oh, sorry, infinite paths arising in HFIE, finite paths whose source is in HFIE, but not in A, and finite paths whose source is in AI, but not in A. So here's the question, when is this a pullback of C-star algebras? Right, so we're looking at this commuting square of C-star algebras, is it a pullback? And this was the question that in the paper of Piotr, Sarah, and Marius that we were trying to generalize. So Luckily, Gert Peterson wrote a paper in which he, as a small piece of it, he characterized when a commuting square of C-star algebras is a pullback. And in our situation with these surjections, we have these two conditions. Right. The ideals at the corners, I1 and I2, should have trivial intersection.
Yeah.
And their sum should be the larger ideal that you divide out to get the right-hand corner. Oops.
One condition. Can you go back to this slide? Where is this theorem? Yes, okay, this slide. So one condition gives you injectivity, and another one gives you subjectivity. Yeah.
Okay.
This is definitely the case. But one quick comment. I mean, of course, we ourselves also always cite Pedersen because it's a very convenient reference. But I bet $1 million that he was not the first one to prove it. This is a general statement about a billion groups, and I bet that people in category theories did it in 118.99. I'm joking, of course, but
yeah, I'm sure you're right. And of course, this is just a small part of Gert's paper.
Yeah,
This
is just a side remark. I mean, he needed it as a technical lemma. He didn't bother to search the literature, so he proved the theorem. But this is a very,
it's true that it persists in this important way because people like me will say, "Oh, Pedersen's theorem about pullbacks."
Yeah, exactly. This is why I'm always sort of making a comment here, because attributing this fact to Pedersen is kind of unfair to category theories. I mean, I bet they sorted it out ages earlier, but Pedersen is such a cute reference, and he has exactly these conditions, and here C-star structure is completely, totally irrelevant. We're just talking a billion groups. This works for a billion groups, and in particular for C-star algebras. Yeah.
Okay, let's see why these things happen. So let's recall our sets U. So here's U1 and U2. And let me recall the set A also, so we have them in place. Now, when you intersect two ideals like this, you're really just intersecting these sets U1 and U2.
Yeah.
So what happens? Well, we know that these two hereditary sets are disjoint. Those are these opposite corners of the three-part picture I had for the graph E. So these are disjoint. These are disjoint. Now, if we look at these two sets, A1 minus A and A2 minus A, their intersection would be A1 intersect A2 minus A, but A1 intersect A2 is a subset of A. So that's empty as well. So the intersection of these two sets is empty. So the intersection of the ideals is empty. Now, if we look at the sum of the ideals, that corresponds to the union of the two sets U1 and U2. Now, let me, there's a better way to do this. Right, there's supposed to be a better way to do this. Right. So here we have HF1E, HF2E. Their union has complement F0. So maybe I could write this HF1E union HF2E. That's just HF0E. Right? It's the complement of the unit of the vertex set of F0. Let's go, where was I? One more. Right, so this is what I've written down here. So the union of these two hereditary sets is the hereditary set corresponding to F0. And if we take these two sets, A1 minus A and A2 minus A, their union is the set A1 union A2 minus A, which in fact is, maybe we remember this one. Where did we see that before? Even my mind forgets. Maybe this is the place where we see it. So something tells me that I introduced this on an earlier slide, but I forget where it was. Anyway, so this A1 union A2 minus A well, so if we throw away A, we're throwing away anything that wasn't in F0 from either of those two. So we might as well be intersecting with F00 before we throw away A. And this set is what I'm calling A12. And I think I defined it earlier, but I can't remember on which slide. But what this means is, let's see. Well, the A12 is a basic feature of one of these sets U. It's the set we put in at this slot in defining this set U. So this says that the I1 plus I2 is the ideal corresponding to a relative Toeplitz graph algebra, where we use this set of vertices. So we write U12 in this way. That's our set A12 that we have. And so the restriction to that is exactly the set I1 plus I2, this ideal. So this quotient by the sum of the ideals is also a relative Toeplitz graph algebra. That wasn't obvious to us before. And finally, of course, we have a pullback if and only if this I12 is equal to that I0, or equivalently if A12 equals A0. So this set A12 here is actually quite important in determining whether we have a pullback. Okay, so maybe here's where I introduced it. Anyway, A12 is this set. It's contained. Oh, this is right. Remember, I said that A0 had to be sandwiched between these two places, and the push out of graphs didn't depend on the choice of A0 as long as it satisfied this. Well, so since A12 is already contained in A0, equality happens if and only if A0 is actually contained in A12, and it's enough to say that it's contained in A1 union A2 because A0 is already in F0. So because of this, we give a definition of what we call admissibility of our push-out data, namely this condition, A0 belonging to A1 union A2.
Just to double check, your alpha i's are injective, right?
Yes, yes. All morphisms of relative graphs are injective on the graph. Yeah, that's part of the data. Yeah, so I'm going to make a comment about that in just a minute as well. But let me just say that all the work we've done up until now has proved our main theorem. So if you have alpha i's to give data for a push out, and we let EA be the push out, then getting a pullback of C-star algebras is exactly equivalent to admissibility of alpha 1, alpha 2. Namely, the set A0 should be contained in the union of the A1 and A2. And equivalent to that is that A0 equals A12 or I0 equals I12. Maybe those are less important. It's the equivalence of A and B that's the theorem we have. Now I want to give some examples. Let's see. So I was going to say something. Yeah, this will come up a bit later. So in their this original paper of Piotr, Sarah, and Marius, they used admissibility in a slightly different way. They were studying a different context. And so maybe let's go back to these 4 conditions. Where were they? Whoops. I don't want to do that. I've messed something up. I'll fix it later. Right. So we have these 4 conditions that tell us what a morphism is. So the conditions for admissibility that those other guys used were essentially giving a description in terms of the graphs themselves, what gives us these 3 properties. Well, mainly these 2, and a little bit more, as we'll see. Let me go back to where I was. I can't remember. That's right, here we go. Okay, now I wanted to just talk about some examples. And just to be, not have to repeat everything over and over again, we're assuming that we have one graph contained into 2 others with these properties that make it a morphism. The complement is hereditary and the edge set is as big as it could be. and we let E be the push out of the graphs as before. So this is before we impose relativizing sets. So the first example is when we let all of the relativizing sets be the empty set, that we're talking about Toeplitz graph algebras. So of course, the empty set intersected with anything is contained in the empty set. So these are all morphisms of relative graphs. And the set A we're forced to define is also the empty set, so that the empty set gives us the push out of relative graphs. And A0 is equal to A1 union A2 because everything's the empty set, so it's admissible. So this shows us that in particular, if we use Toeplitz algebras throughout, we get a pullback of C-star algebras. I'm sure this theorem is easily proved independently of this machinery, but it's just this, I was trying to investigate as examples the two extreme cases that are possible. So this extreme case is quite easy. The second extreme case is much more interesting. So I'm going to spend the rest of the time talking about this one. So what happens if we try to use graph algebras everywhere? In other words, we want A sub I to be the regular vertices at Fi for all three graphs in our initial data. Okay, so that the relative Toeplitz algebras are the graph algebras. So in order to have morphisms for the 0 into the F0 into F1, we have to have the regular vertices of Fi that are also in F0 should be regular in F0. So for example, let's take a vertex that's regular in Fi, it's in F0, 0, and maybe it's not regular in F0. What would that look like? So this means that it's regular in Fi, so there's a finite non-zero number of edges coming into V. It belongs to F0, but there are no edges in F0 that go to V. So it's actually a source of F0. So the picture looks something like this. So we can't have that if we want to have morphisms of relative graphs. And that means that we have to rule out this possibility. And ruling it out is another standard property of graphs, namely saturation of the set H. So we can now give that definition. A subset of the vertices of a graph is called saturated if you have a regular vertex and all of its edges arise in the set H, then the vertex V must also be in H. So exactly when you have this picture, V would have to actually be over in H somewhere.
A quick comment about saturation, if I may, because we are so lucky with hereditary subsets that it defines for us a useful topology. So you might think that you have this natural saturation property, which is very important because, in fact, when you have an ideal generated by a set of projections, you should saturate the set of projections. I mean, it's always the same as the ideal of the saturation of a set of projections. So it's very natural from this point of view. So you might think that just like you can define Kuratowski style, the topology not by a family of open subsets, but by the closure operation. So if you replace the closure operation with a saturation operation, unfortunately or fortunately, I know, just a fact, it's nature. It does not define topology. So hereditary property does define topology. It just gives you family of hereditary subsets can be viewed as a family of open subsets defining a topology. But you cannot think about saturation property as the closure property defining a topology.
That's very interesting. So one thing that we discovered. Sorry?
Say it again now.
Is it because it's not stable under taking size from you?
One of these conditions. I don't remember which condition, but we checked it. I mean,
it's obviously not important.
Yeah. Oh, yes, obviously not important. Yeah. Of course,
it's interesting.
The saturation is that's obvious, but one of these properties making it topology fail. Yeah, but that well might be what you just said. Yeah.
I was trying to see why it fails. Stable and taking finite.
Yeah.
It's also preserved.
Yes.
It must be that property.
Yeah, if these three properties, inclusion preserving is obvious, idempotent is obvious, so it must be the third one. Yeah, I agree.
You have an easy example showing.
Well, maybe not offhand. I mean, it's but it's not complicated. I did it in my lecture course. So if you go to YouTube recordings,
you try to prove it, you will find.
Yeah. Yes, exactly. Exactly. And I might have explicitly such counterexample in my lecture notes. Okay. Okay, sorry, Jack. Just a little
That's all right.
internal discussion.
It's interesting because one of the things we discovered in doing this that the hereditary saturated sets came up in studying the ideals of the graph algebras.
Exactly.
Right? And what of course, it takes us a long time to unlearn things that we learned as infants. Saturation really is only relevant when you're talking about the graph algebra.
I agree.
So hereditary is crucial in all situations, but the
I fully
saturation
agree.
somehow has to do with this special thing. And that I wonder if that has something to do with why you were running into problems with this topology.
I fully agree with this comment. When I was defining saturation in my lecture course, talking only about graphs, okay, I had to sort of apologize. Said, look, I'm defining this weird property, but from the point of view of graphs, you don't know why I'm doing it. But with hereditary, this is necessary. I mean, basically, with this standard procedure of getting a subgraph by removing some vertices and removing, in your terminology, all edges that start at these vertices. Okay, in order for this to be a subgraph, you must have a hereditary property.
Right.
It's just if and only. But saturation is sort of irrelevant. But it is highly relevant
at that level,
of ideals.
Right. When you restrict to the boundary, then all of a sudden the saturation becomes relevant. Okay, so the consequence of this is that we have to assume that these hereditary sets are also saturated for the F1 and F2 in order to have morphisms in our category. And as we were just describing them, this is a typical feature of when you're working in the graph algebra. So we make this assumption, and then we do have the data we need for constructing a push-out of graphs. Now, I thought I should go back to that picture again. This is obvious, but one of those things that's easier to look at, I think. Right, so here we have HF1E, that's E minus F10. So here's F10. Maybe I should try to do this a little differently. Okay, so here we have, this is all F10. So here we have E minus F10, E0 minus F10, that's the HF10. But you could also think of it as, so maybe let's go back. So this is E0 minus F10, but it's also F20 minus F00, because the whole left-hand side is F20, and now we're throwing away this portion F00. So what that tells us is that HF1E is the same as HF0 F2. And that also works in the other side as well by symmetry. Okay, let's go back to wherever I was. I should have checked the page number. Let's see. That's pretty good. This is what I'm recalling here. So HF2E is the same as HF0 F1, and likewise HF0 F2 is HF1E. So it turns out it easily follows these are also saturated in E as well as in F1 and F2. So if we're looking at the inclusions of F1 into E and F2 into E, we have saturation there as well. And we really just have to check this condition on the relativizing sets, that the regular vertices of E intersected with Fi0 are contained in regular vertices of Fi. So let's consider a vertex V that's in, say, it's regular in E and it's in F1. If it weren't in regular in F1, it would have to be a source in F1, right? It's regular in E, so it is definitely a finite receiver. So the only way it can be singular in F1 is if it doesn't receive anything in F1. But then it has to receive everything from the complement of F1. but it's regular. So this would violate the saturation that we've already noted is existing. So in fact, that's our proof that this is true. So there's a check mark. And so in fact, we do get morphisms, and our push out makes sense. Well, our commuting square of relative graphs makes sense. Now we want to know, do we have a push out in the relative graphs? And for that, we have to check, right? This is the set A and these three different pieces that the A has to be. So these are what we have to check. Let's see, I have something about this. So here's again the condition we have to check. So I've drawn each of the three pieces of that set on the right in our picture of E here. Those are these gray portions within the three portions that E0 has been divided into. Now, say if we look at H, this whole upper square, not just these things. If a vertex in this square is regular in E, that can only happen if it's already regular in F2, right? This whole thing. Right. Let's see, so that's because there are no edges going this way, right? These things are hereditary. So any vertex here can only receive edges from this same place. So being regular in the whole thing is the same as being regular in the left half. Likewise, being regular here is the same as being regular in this lower portion. So regular in F1. But to be regular here, it has to be regular both in the left side and in the lower portion. So it has to be regular in both F1 and F2. And this tells us that if we have something regular in E, well, depending on which place it belongs to, it has to belong to the gray portion in each of those places. And that's exactly this picture. So this is supposed to be a diagram. Oh, what's the name of this guy that draws pictures to show you proofs of things? I can't remember. Anyway, this isn't as good as his stuff, but it's supposed to be a step in that direction to see why we do get this condition giving us a push out of relative graphs. And finally, we have to consider the admissibility. So here's our condition for admissibility, A0 contained in A1 union A2. Now, if we rewrite this, that says that the regular vertices of F0 are contained in the union of regular vertices of F1 and F2. Equivalently, if we intersect regular vertices of F0 with a complement of that union on the right-hand side, we should get the empty set. But the complement of this union is the intersection of the complements. Those are the singular vertices of F1 and F2. So admissibility is equivalent to saying that a regular vertex in F0 cannot be singular both in F1 and F2. Well, since it's regular in F0, we know it's not a source. So singularity has to mean being an infinite receiver. So a vertex that's regular in F0 cannot receive infinitely many edges, from both of the two hereditary pieces in the corners of our picture. And so this is a stupid way of saying this. The technical term for such things is that V cannot be a breaking vertex for both of those hereditary sets at the same time.
Yeah.
Okay, so this is what we get. This commuting square of graph algebras under our hypotheses about saturated hereditary sets and admissibility. It's a pullback if and only if we have this property about the singular vertices. So this was a theory, well, in this case for the graph algebras, this was a theorem of Piotr Serra and Marius. It was a slight generalization of their theorem. But Piotr sent us recently a preprint with Marius that generalizes this, at least in the case of the algebraic case. And also, this is the rank 1 situation, and the rank K situation was treated by Alex Kumji and David Pask, Aidan Sims, and Mike Whitaker when they have a remarkable paper for higher rank graphs that does a lot more than what we're doing here. Okay, well, so if we don't use this restriction.
But speak up so that they are heard.
So what do you mean by the rank of a graph?
So So Alex and David introduced this notion of higher rank graphs.
Yeah. So what's the rank?
The rank is the higher rank graph, the length of a path is measured in a k-fold Cartesian product of natural numbers. Whereas an ordinary directed graph, the length is measured as just a single natural number. So the rank is that exponent n to the k, where you measure the length of a path in the higher rank case. In fact, you could describe their idea as, observing that the length of a path for a graph has a unique factorization property. If you factor the length as a sum of two lengths, there's a unique way to write the path as a composition of two paths of those lengths in that order. So if you generalize that to having a small category with a homomorphism into n to the k, it has the same unique factorization property. That's what they call a k-graph. And remarkably, it's unbelievably more complicated than the case of one graphs. As soon as you hit k equals 2, it just explodes in terms of how messy and complicated it is. Well, that's my picture. People who like it think it's the most beautiful thing in the world. I find it very hard to work with myself.
But let me comment. You see, you can think about the rank as the number of colors. So imagine that edges have also colors. So you have the subset of green colors, of red colors, and the number of colors is the rank of your graph. And so you can ask, why bother? Why do you generalize to such a setting? You see, one of the big drawbacks of graph sister algebras is that they are ostensibly, not conspicuously, not closed under the tensor product. Tensor product of graph sister algebras is not a graph sister algebra. Unless you take trivial, complex numbers times complex numbers, yes, it's complex numbers again. But short of such trivialities, are not closed under Cartesian, the tensor product. Whereas with higher rank graphs, and this is what Sarah Resnick taught me, you have a special way of making, you make it a monoidal category, I guess. So there's a nice recipe of having a Cartesian product of a K graph and then L graph. And the Cartesian product of a K graph with an L graph is a K plus L graph. And now, lo and behold, now it corresponds to the tensor product of higher rank graph sister algebras. So
basically, if you take tensor product of sister algebra, you just raise the rank.
Exactly, add the ranks. Yeah. So and that's very beautiful. And it comes immediately with some very natural examples. I didn't want to have anything to do with higher rank graphs, but we had a natural example, and then it turned out, of course, it's not the graph sister algebra, but it's a rank 2 graph sister algebra. And then in colors, all of a sudden, I could do it. Okay. So that's very, very, very nice. And I think also having these colors allows you to have some theta twisting, right? Because somehow you can have this additional commutation relation, like in a non-commutative torus between different colors. Yeah. And
of course, there's twisting in ordinary graph algebras, but the scope is larger for higher rank graphs. I should also say, I always begin saying things about higher rank graphs by saying how I think they're messy and complicated, but of course they are very beautiful and they are very important in lots of ways. Though I guess most of my recent career has been in trying to give generalizations that are make it a little bit easier to work with.
Yeah. Okay. Thank you.
Okay, so I have one more slide actually. If we drop that restriction on the singular vertices, namely that we allow a regular vertex in F0 to receive infinitely many edges from both of the hereditary subsets, we can still get a pullback, but we have to go back into the category of relative Toeplitz graph algebras. So namely, we have to replace A0, instead of using all regular vertices in F0, we have to throw out the things that are the problem, right? That are breaking for both hereditary sets. And if we do that, then in this corner, we replace the graph algebra with this relative Toeplitz graph algebra, and then we recover having a pullback C-star algebra. Okay, and that's all I wanted to say. So I have a couple slides of references, but Piotr asked me to send him the slides. So when I post them, if you want to look at that, you can.
Yeah. Okay. So thank you very much. Now I have plenty of time for questions, so please go ahead. First, maybe in Warsaw. Any questions in Warsaw?
You do it for finitely many graphs. Consider on the pullback side of the graphs, on the push-out side of the graphs, you consider the inductive limit, and on the system algebra side, you consider the projective limit for finitely many relative in your setting relative to Toeplitz topics.
I'm sorry, I didn't hear the question. I
For
was drinking
example,
some water.
take an exact case. Now you have three of them. You consider not only the pullbacks, but a general finite projective limit, but for finite many objects and finite many morphisms. And
That's a good question.
Reference in that.
Yeah, I've not thought about this at all. That is a good question.
Yeah.
Yeah, so we only looked at this pullback construction. We were very limited in our imagination. But yeah, that's a really interesting idea. I don't know what happens.
Yeah, but it's very natural because such things are definitely considered in the context of graph algebras. Okay, so and one thing you can add that somehow it should have implications for multi-pullbacks. When instead of having an agreement of say two pieces over one piece, you have agreement of n pieces over whatever m other pieces. Okay. And one of the things is with multi-pullbacks is that you can construct them as iterated usual pullbacks. So sort of, if you think about gluing spaces together, if you want to glue n pieces together, you can just glue first two pieces and then glue the third piece and so on and so forth. So following this intuition, you can consider multi-pullbacks as iterations of usual pullbacks. So I guess generalization in this direction should be immediately doable. But I fully agree that one should consider general, limits, not just this is a very particular limit. Yeah.
Actually,
yeah, no, I think your idea of
how if I pose some nice conditions on a graph, like in this one, so it meets always the mid pullbacks. How far can the category of Toeplitz graph algebras is from elementary topos?
Oh, this I don't know.
This is why I start with the question. Finite projective limits.
Tomek, you know about toposes. Can you answer this?
Yes, but first I would like to comment on finite colimits. Finite colimits are generated by double colimits, and you need also quotients.
You also need a sub-object classifier, right?
No. I'm not talking about toposes. Now I'm talking about general colimits in a category. If you allow finite colimits, then the finite colimits are generated by double pushouts and quotients. So this generalization would require an analogous theorem about quotients. Okay, so about toposes, I don't know if this is so relevant because toposes are higher structure. So this is about spaces, in fact. So the meaning of this theorem is that you have a category of graphs, and you have something like noncommutative realization functor to the category of noncommutative spaces. If you reverse arrows formally, then you obtain opposite category of Sitter algebras regarded as noncommutative spaces, and then your construction is a functor preserving pushouts. I would have a question in this context, because there are many similar theorems. For instance, in algebraic topology, when you have the Van Kampen theorem. Okay, if you have fundamental groupoid, then you can say something about the convolution algebra of the fundamental groupoid in terms of one skeleton of your let's say CW complex. And then in the Van Kampen theorem, the push-outs of groupoids appear. You are going from graphs through groupoids to sister algebras. So the natural question would be, can these conditions for admissible morphisms of these graphs, can they be rephrased in terms of groupoids? And then how all this business is related to push out of groupoids?
Yeah, interesting. So in this passage that we're using here from graphs to groupoids is contravariant also, right? Because you're restricting the groupoid to a subset of the unit space. Well, let's see. So I'm not very categorically minded. So I suppose you could say that the subgroupoid is, the groupoid of the subgraph is a subgroupoid of the larger one. But I think of the, well, I don't know. I don't know the answer to your question.
My question
the groupoid is supposed to, is really much closer to the C-star algebra than to the graph. It's supposed to give us some more, in the same way that if you have a homeomorphism of a compact Hausdorff space, and you proceed from there to the cross product C-star algebra of the corresponding automorphism on functions on the space, really the space to the C-star algebra is an equivalence. So we're really thinking of, it's almost the same thing as working in the C-star algebra, whereas the graph feels like a much more fundamental object that's in a really different place. And we're somehow using that to code something about this other structure. So I'm not sure that push out of groupoid is what naturally would come out of this kind of thing.
I think I agree with you, because passage from groupoids to groupoid sister algebras is covariant, right? That's covariant. It's like a group sister algebra. This is a covariant passage. So because the passage you are discussing right now is a contravariant passage from graphs into graph sister algebras, I fully agree with how you answer it. So then the question, Tomek, should be more about how push-outs of graphs relate to pullbacks of groupoids.
No, because Jack inverses arrows in a sense. Your formalism, in your convention, you have some orientation of arrows. So here we have, in a sense, the composition of these arrows is opposite.
But I don't think it has anything to do with covariance versus contravariance. I think that's irrelevant.
Yeah, I think Piotr's right there. The particular convention for drawing paths in a graph is
irrelevant.
Just a way of coming up with relations in a C-star algebra that are completely equivalent. It's just a matter of taste.
But I'm not talking about the properties of this functor. I'm talking about the relation between graphs and groupoids.
Yeah, so I think
this preserves arrows. It's not contravariant.
Let's see. So if you have a yeah, I see your point. The subgraph corresponds to a subgroupoid in the sense that you're restricting the larger groupoid to an enclosed invariant subset of its unit space. So yeah, it's this question, if you have a closed subset of a topological space, yeah, no, I see your point. I'm not sure how the push out of the graphs would relate to a push out of the corresponding groupoids.
Maybe it's not a push out, but my question was much simpler. Because I was asking, in fact, about how to rephrase this condition for morphism of graphs,
these relative graphs, yeah,
or relative graphs in groupoid terms. because
Yeah, so
it is well, it is this problem you mentioned is very well known, and in the language of groupoids, there is a solution to this problem about contravariant versus covariant, which is called the Zakrzewski morphism.
Mhm.
So it is not a big problem, but to interpret this your conditions for morphisms of graphs in terms of groupoids.
Might you be asking something like the following? If you have say have a groupoid, choose a closed invariant subset of the unit space. When does that correspond? When should that be called a morphism of groupoids? The inclusion of the restriction into the larger thing. For which closed invariant subspaces should that be considered such a thing? Is that the kind of more explicit question you're thinking of?
The definition is quite complicated, but it is done by Zakrzewski, and there is a survey about this by Stachura.
Uh-oh, something froze for me.
Can you hear me?
Oh, no, I can, yes.
Yeah, we can hear you.
But this is another problem. So my problem was to understand these morphisms in terms of because not all combinatorial morphisms you could imagine between graphs are allowed.
Yeah.
You have very strict conditions on these things. So my question would be, can you interpret these conditions you impose in terms of conditions for this groupoid?
Yeah. Let me think.
Somehow it must be hidden in your work because you are using these groupoids effectively. So it must be some reason.
But if you just look at the groupoid without thinking about the graph structure that gives rise to it, I'm not sure how to describe what's going on there without that.
Well,
so it's all a matter of, yeah, go on.
Let me answer it at least after a fashion. You see, I'm not very much used to this picture of a groupoid, but when you want to think in terms of sister algebras themselves already, graph sister algebras, relative or not, basically this condition, these very strict conditions of what morphism between graphs would induce a star homomorphism between sister algebras, that's exactly here where these restrictions are needed, because somehow when you have this morphism of graphs, then you see how it induces things at the level of sister algebras, but then for this induced thing to be well defined, to respect this ideal given by Kunst-Krieger relations, you must impose these conditions. So if you want, these conditions that you have on morphisms are imposed by Kunst-Krieger relations.
Yes, because the morphism was exactly defined to correspond to these quotient maps of Kunst-Krieger or Toeplitz.
So for instance, if you would just do path algebra, so no Kunst-Krieger relations whatsoever, right? Then the only condition you have that your morphisms are finite to one, that's it. Any finite to one morphisms of graphs would induce contravariantly a homomorphism of path algebras, any whatsoever. Forget any hereditary, nothing is important.
Yeah. And this you cannot rephrase in terms of the groupoid of the graph.
This I have no idea, but if really groupoid is very, very close to a sister algebra, then somehow in order to really have the induced morphism of groupoids, forget which way, covariant or contravariant, you must satisfy some properties of a groupoid, that it is a groupoid, that some things are not violated. And I guess that this imposes on you the conditions on what morphisms of graphs are admissible and what are not. Mm-hmm. Right, Jack, would you agree?
Yeah, that sounds right to me.
Yeah.
It's very nice because the condition on the groupoid to or morphisms of groupoids inducing star homomorphism is precisely this Zakrzewski condition. So maybe this is not so far from this Zakrzewski's condition.
I would believe so. Yes, this is a very nice question.
Can you send me the reference to the Zakrzewski?
Well, not now, Tomek. Just send an email to.
No,
Jack.
Good.
yeah, it's not in real time. Yeah, but eventually.
No problem.
Yeah, because I'm not so familiar with these categorical questions. We basically invented this category, as Piotr said, exactly to model these maps of relative Toeplitz graph algebras, and saw that it was a perfect mirror for that, and then wanted to give some combinatorial version of what the pullback would be doing.
Yeah. Tomek, your hand is still raised. So
I forgot.
do you want to ask another question?
Right.
No. I'm satisfied. Thank you very much.
Okay, anybody else from the Zoom? Well, if not, then allow me to ask a question, make some comments, but I will need to write. So I will now start whiteboard. So I do share screen. I start the whiteboard. Okay, and you should be able to see it. Okay. I put it here, I enlarge it. Okay.
Okay.
You will not see me, but you'll see my writing on the board. So first, let me make a very quick comment. I would like everybody to appreciate, I know it is just an exercise, but the result that this category which Jack is considering is called on the push out is non-trivial. I mean, it's not a vacuous statement. And let me give you the following example. If you consider graphs, but in the category in which all morphisms that you allow are only phi next to 1. Sorry, so this is exactly what I shouldn't write. Where is this? Eraser. Okay, so take morphisms that are phi next to 1. Then this category is not closed under push-outs. And I encourage you to construct a counterexample because it's quite a lot of fun. It's very non-obvious to begin with. It's a beautiful exercise. Okay, so for instance, to remedy the situation, because you have to be phi next to 1 to induce the reverse homomorphism between path algebras of these graphs. In order to consider push-outs, we have to assume that at least one of these morphisms, whichever one you choose, is injected. Yeah, if one of these two morphisms is injected, then indeed you can complete it into a push-out diagram, and these also will be finite points. Of course, push-out exists in the category of graphs, okay? But the thing is that if you restrict your defining morphisms to finite to 1, these errors that you obtain here will not be finite. That's why I'm saying that in the restricted category of morphisms are only finite to 1, and push-out does not exist. So we had to remedy it by going to the setting when at least one of these maps defining a push-out is an injection. But this is not such a big trouble because it's very natural from the Meyer-Vittoris perspective. Okay, if you want to apply the Meyer-Vittoris principle, then you must have that this is what one injective in a push-out, or if you dualize now to algebras. So imagine now that we talk sister algebras, and we have a pullback of sister algebras. In order to, for instance, have this pullback inducing for you the Meyer-Vittoris 6-term exact sequence in K-theory, at least one of these defining arrows has to be surjection. Otherwise, you don't have the Meyer-Vittoris in K-theory. So that's not a very painful assumption. And also as a sort of sneak preview of Mariusz's talk in 2 weeks. So in 2 weeks, Mariusz will give a talk about our new paper, which you mentioned on one of the slides, this new paper. And basically, our generalization, if you want, goes in the direction in which we still prove the pullback theorem, but we assume that only one of these morphisms is surjective. If you want at the level of graphs, we assume that only one of these admissible morphisms is really injective, but the other one is not necessarily so. And one of the reasons why I like it is that indeed you have plenty of new natural examples. I mean, this new theorem, the generalization, is not just for the sake of being ever more general. You simply have very natural life examples in which you have a push out, which is only one injective, not two injective. Okay, this is too much to add that you only consider injections. This kills a lot of very important and natural examples. And by having this push out, which is only one injective, then our pullback is of course only one surjective. And I repeat, this gives us very, very nice examples in which we still can claim that we have a pullback sister algebra over here. Okay, so this was my comment. Now let me ask you a question. It's about your theory of relativity. So whenever you have a relative graph, so well, I don't remember what your notation was. So
E comma F comma A or something.
Let me notation I'm using. So X is a subset of regular vertices in graph E. Okay.
Okay.
So for me, this is a relative graph, and yes, of course, I agree that when you have a morphism between two relative graphs, it's the usual morphism between E and F, but you have this additional condition that X must be somehow contained in Y or stuff like this. Okay, but here it's also very standard. It's in this book you cited about Levitt path algebras. By these three authors, Abrams and others, is that whenever you take, well, they talk about cone path algebras and Levitt path algebras, but I bet it's exactly the same on the sister level when you have Toeplitz algebras and graph sister algebras. And this is a very remarkable fact. So whenever you have a relative, you take this, say, sister algebra, I mean, they do without the completion, okay? But when you take, say, the graph algebra of a relative graph, EX, so Toeplitz or cone, okay? Then you can always construct a new graph. This is not a relative graph, that's the absolute graph. You can construct a new graph EX, so you have a sort of recipe to turn relative graphs into graphs, so that these two graph algebras are isomorphic. Okay, and let me give you a very standard example. If you take as a graph just one loop, this is my graph. Okay, so if you would take, if you would look at it in this recipe of having Toeplitz, so I think then your notation was T C star, right? Then this is really the Toeplitz algebra. I mean, this is the reason why you call it Toeplitz graph sister algebra. Okay, but if you would take just the graph sister algebra of this one loop graph, that's of course the circle algebra. Okay, but using this recipe, I'm not sure I remember it correctly, and please forgive me, I will use my convention, not yours.
Yes.
But the recipe is, if I remember correctly, as follows: that you look into your graph and you look at all your sinks. In your case, it would be all your sources, right? And then you double you look at regular vertices, and then you double your regular vertex. And then for every regular vertex, you draw additional edge, which would go. So if you have a regular vertex, it cannot be a sink. It must emit some edges. and somehow you also double these edges. Because this regular vertex emits an edge, okay, so somehow you must also have an edge which is emitted from this double vertex to this vertex which you have there. Graph is something like this. And now, well, you see this theorem. So this is my graph E. This is my graph EX, okay? And now you can see that indeed the Toeplitz algebra can be written as a graph sister algebra of this graph written like this, okay? So that's an exemplification of this beautiful theorem. It's completely general. There are no assumptions whatsoever, okay? So if you want, this theorem of relativity has the speed light equal to infinity. I mean, somehow you don't see these relativistic effects. I mean, every Toeplitz algebra is a graph sister algebra, but for a different graph. So in this context, somehow can we translate, I mean, maybe I'm just being naive and missing something. Can we translate everything we do in Toeplitz algebras using these relative graphs? Can we reduce it back to the usual things? I'm not sure. It's not so completely obvious because this recipe of going from E to EX is not so completely, it's not so completely trivial. It's actually quite complicated. And it takes quite a bit of work. I mean, this is not a difficult theorem. It's just very lengthy. Seeing it through, yeah. It's a number of...
Yeah, so, of course, this construction you're describing for the graph sister algebra is goes back to the paper of Bates, Hong, Rayburn, and Szymanski, where they built this extra graph to realize one of these intermediate quotients by an ideal. And then in the paper of Eilers and Katsura, they exactly give this construction for the relative Toeplitz graph algebra, exactly as you're describing, by building the new graph for which you actually get a graph sister algebra. And I guess, so I have sort of two things to say about it. The first one is that we felt that the relative Toeplitz graph algebra construction was more natural than building this new graph by what feels like a somewhat ad hoc manner, even though they're completely equivalent. But as to your actual question, can we rewrite the Pullbacks result entirely in terms of the new graphs? I would be really surprised if that weren't possible. Mm-hmm. I've not thought about doing that, but it seems like there's this process for changing the graph would allow you to describe exactly what's going on. I don't know. Yeah, that seems like a very reasonable thing to do.
Okay.
And I would bet probably along with you that that's possible.
Because one should be able to translate. I mean, well, it is a one-way street. I mean, it's not like it works one way. You can present every Toeplitz algebra as a graph sister algebra, but I'm not saying you can do it the other way around.
No, you put conditions on the graph that says it's been obtained by this way. That's why it seems a little bit more
I mean, not
difficult
graphs,
to work with.
Exactly. Yeah. Not all graphs are received like obtained like this. Yeah. I agree. Yes.
Yeah.
Since I have
I don't see why there shouldn't be some corresponding theorem in that using that way of describing the algebras.
Yeah. Okay. So, are there any other questions? If not,
maybe I could have a comment about what you said lastly. In classical topology, if you have pushouts, then you can not always you can modify what you are gluing to obtain the same result. Okay. But you can have a series of modifications, because instead of a single pushout, you can have a series of pushouts, and you can pass from one to another by some sequence of moves, and the resulting gluing is the same as because what you want here is something like contracting a subspace, closed subset of a space. Okay, and then you are asking whether the result is of this contraction of something doesn't affect the gluing of spaces. Sometimes it's possible, sometimes it's not. But even if it is not, you can create a sequence of push-outs interpolating between these two constructions. So if you remember, Piotr, in our Waldhausen paper, we have push-outs describing almost everything, all constructions. So contractions of a subcomplex is a special case of this. Yeah. So I wouldn't expect that in case of graphs, the situation would be much different.
I'm not so sure, but I take your point. I think here it should be more straightforward. I would be more optimistic because somehow every relative graph can be viewed as a certain specific graph from the point of view of graph history algebras. So it's just a question of translating the conditions you have for relative graphs to conditions that you would have for these absolute modified graphs. They are more complicated graphs, and here the real challenge is to see. But by the way, a good project to make an exercise in algebra, graph history algebras, to see whether these modifications, because they are substantial, okay, how do they relate to these admissibility conditions? Okay, and I take admissibility conditions for a relative graph. I create EX and I translate these admissibility conditions for these, because this assignment is a functor. So going from EX, from E comma X to EX is a functor. We proved it in our class. It is a functor. Okay, so this is it's a complicated assignment, but it's not ad hoc. Yeah, I repeat, this construction mapping relative graphs to absolute graphs, going from E comma X to EX, this is a functor, it's functorial, it's natural. It respects morphisms between relative graphs, we use morphisms between absolute graphs, okay? So this is very good. And now one should be able to translate these admissibility conditions for relative graphs to admissibility conditions for these absolute graphs and see if they match. And if they match, then here you go. I mean, basically, that one theorem is reduced to the other. Yeah, that's how I view it. That would be a very nice exercise. Okay.
So you mean there is no need to modify this admissibility?
I don't know. This is completely open question. I mean, I have no idea. You want these conditions of admissibility are a little bit of a mouthful, so you really should look at it. I cannot, even though I'm very, very much familiar with them, I cannot do it just ad hoc in my mind.
Yeah, so essentially in my comment, I said that in other situations, such adjusting this condition would require a change. But you say that in case of the passage from relative to absolute graphs, such change would be not necessary.
Exactly, and I would
maybe.
Yeah, and I would be kind of hopeful, you know, Jack. I think what might happen is that because relative graphs are in fact special classes of absolute graphs. Okay, I mean, I know it's kind of funny, but via this functor you can view it this way. Then it might happen that there will be special graphs. Your admissibility conditions are a little bit relaxed. So I bet that the admissibility conditions for relative graphs would translate into some subset of admissibility conditions for absolute graphs, but it might be a proper subset, and would be a beautiful game because you can say, aha, for these specific absolute graphs, I have relaxed admissibility conditions that would still yield a pullback of sister algebras.
Yeah, so the admissibility condition we give for relative graphs says something about the sets that you relativize with. So if you look at the corresponding absolute graphs, then it would seem that the admissibility condition would have to take into account the fact that those are obtained by this functor from relative graphs and have something to do with a certain substructure of those graphs.
Exactly.
And so if that were washed away by the general admissibility conditions, that would be sort of interesting, yes.
Okay, so do you still have some?
I have a very naive question.
Sure.
Does any Toeplitz theta algebras of a relative graph arise as the Krieger-Kunz algebra of a graph?
I guess that's what I just said over there.
So that seems a bit weird to me because the theta algebra of a graph is always nuclear, right?
Yes.
Yes, I think it's true. Yes.
On the left side, I don't see it. There might be some Toeplitz algebra, but it's not nuclear.
Well, I mean,
Oh, no. The relative Toeplitz algebra, the Toeplitz algebra graph is also always nuclear.
Okay.
yeah.
Well, oh, because as Piotr said, it is the graph algebra of a relative of a different graph, and then the idea the quotients would follow the same way. Yeah, so that this one saving grace in this business is no worries about nuclearity.
Yeah. Okay. So let me stop recording. I stopped sharing first. Stop sharing, and now I stop recording.